Alrighty, well, happy Thursday. We're going to keep talking about linked lists. This is gets to be a little bit interesting, right? When we start looking at how we work with data in different data structures. We start talking about how fast things are or how slow things are. And this idea of the performance analysis, trying to see are our algorithms going to be quick or slow based on how much data is in them. And that's usually what we care about. It's all based on how big these data sets are that we're working with. So it's all based on the n number of sizes here. And I did finish getting this circular doubly linked list working here. Turns out when you copy paste stuff, you have to rename more than just a few things here. So if you take a look at the GitHub history here for this one, I just needed to actually change the name of the constructor in the class, so that was good. And then logic errors worked for me instead of runtime errors. I don't know why the other wasn't, but it worked when I switched over to that, so that was pretty happy. Then I could get my circular doubly linked list working, where I can add to the first, add to the front, add to the last. So add first, add last, this idea. So from either end now, I can add to this data structure that holds these nodes, and each of the nodes then, remember, knows what comes before it and what comes after it. So this idea that I can follow the links here. So one of the things I want to talk about was the lab exercise. What the goal of that was to be able to go traverse this list and print out every item going forward or print out every item going backwards, kind of around that link. So if we put in, I don't know, what do we had, like 4 and 7 and 9 or something here, right? So we had our little dummy node at the top. Sure, that's with one M. That's probably good for how do you spell dummy, because, come on, really, Word? Okay, Word wanted to crash on me here. So the dummy node, the next of dummy node is always the first item. So its next would really kind of point to the 4 here. To imagine that as a circle, if you want here. It gets to be a little funny, but that's okay. And the previous of dummy node is always the last thing here. So that one always points to the 9. And each of these then point to each other, right, with next and previous. So to traverse the list, if I want to go forwards, I'm going to start at dummy node and go next, 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 until I hit dummy node again. To go backwards, I'm going to start at previous and keep going previous, 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 until I hit the dummy node. Right? So I can add in some functions here to this, like, I don't know, what did I say? Void print forward here. So to print in the forward direction, I want to start with a current node. So when we have these linked objects, we're going to have one, and then we're going to make that one go to the next, and go to the next, and go to the next. Right? So I don't think we did that with any of these ones here, with the singly linked list here. Let's see, did we do it with the, I don't know if we did it with this one either. We never had to traverse any of these here. So what we're going to do is we're going to start with the current node. So I'm going to have a node of T, the current node. It's going to start as the dummy node's next. That should be the first item in the list, right? Node of T pointer, right? Current node, we've got dummy nodes next. So I'm going to have the pointer to a node, and then I can say as long as this is not the dummy node, right? That's going to be my loop here. So my dummy node here, I want to keep going until I'm not reaching the dummy node. So I can say while my current node does not equal the dummy node. Right, so keep on going as long as I haven't got to the dummy. So if there's no items, this doesn't run at all. So when we create our original doubly linked list here, with no items, dummy node's next is itself. Dummy node's previous is itself, because it's empty. So as we start adding items, we just keep adding in between. To add to the last is between the dummy node and the previous, dummy node's previous, which is the old last thing. To add to the first, what comes after it is what used to be first, and what comes before it is the dummy node, right? To insert into those links there, right? So while it's not there, while it's not none, I can output then the current node's data, and then, I don't know, maybe a space. I didn't really specify how we wanted to do all of this here. So just output whatever data that node's looking at, and then I'm going to take the current node, I'm going to say, okay, you go to the current node's next. So we're this idea of you kind of like walk the links here. You would say, okay, who comes after you? Okay, who comes after you? Okay, who comes after you? Who comes after you? Who comes after you? And we just traverse all of these lists, all the links here as we go. To go forward, eventually we'll hit the dummy node and the loop should stop. And maybe then I'll output an end line. Right? So printing in reverse is basically the same idea. So what did I say? I think it was print backwards here. But we're going to start with previous because we want the last item in the list. And instead of going to the next one, we're going to go to the previous one. Just keep on going backwards as we go. So start at the end and ask what comes before you, what comes before you, what comes before you, what comes before you. Or going this direction for you guys, right? If you imagine that as a big circle, right? Going that direction. So we should be able to print these forward and backwards, then in the list. So if I pop them off, I'm going to lose them here. So before I pop them off here, I'm going to try and print my circular W linked list. We'll say print forwards. So it should be 2, 3, and 4, right? Because we added 2 to the first, 3 to the last, and then 4 to the last here. And then we should be able to print them backwards. Print backwards. Again, outputting things is going to be really hard to test because we're not returning values, but that's okay. So we're just going to throw it out on the screen here and see if that works. But if you want to watch it in debug mode, you can actually watch it traverse those links as we go, which is really fun. So I can say, okay, let's start. Let me jump into my code, right? I want to step into this function here, and now we're in the print forwards function, right? So the first node, my current node, will be the dummy node, right? This is the dummy node, right? This has a dummy node, and now I am the dummy node, my current node. So it's next then, and it's next, and it's next, and it's next. Eventually, I'll get to the dummy node again here when we go. Right? Because it will just keep on looping forever. It's a circle. So in the debugger here, you can just keep opening these up here and you'll just go forever. We know that this one happens to be the dummy node, right? Its value is 0 and it is ending at 2DD0. 2DD0 is the dummy node. We can see its memory address, right? If you want to get that, like this is where that node is stored in memory somewhere. But we should be able to watch this and it keeps on going and then current node will change, right? Because we're going to the next one. And the current node changes, and current node changes, current node changes, and then we're done with the loop because current node hit back to dummy node. We completed that full circle here, so we should have 2, 3, 4. That worked. That did what we expected it to do, which is pretty good. We'll try going backwards, right? Same idea, and now we'll get 4, 3, 2. We hit back to the dummy node. We've got it printed backwards, 4, 3, 2. So we just kind of walk these links as we go. So the other cool thing we can do, right, so this will be, if we looked at performance, right, how well do you think this one performs to go and print every node out in terms of n size? How many operations is that going to take? If we have to touch every node, it'll probably be n, right? Because we have to go through every single node in the list to print it. Right, same with this one. Well, then you have to print every single node. Now, what if I wanted to get something out by index? What if I wanted to get the data out? What is it, like make an at for an index here? Right? Pretend like we're a vector, have an at function, so we can get a value out. Now, we don't have a way to set these currently, but that's okay. We can figure that part out later. But to get the data out at a given index, well, we need to start at the current node, right? And now we're not going to output here though, right? And we don't even really want while we're not the dummy node, right? We don't need to loop until we're not the dummy node. We just want to keep going until our index matches, right? So maybe we have a for index is, current index is 0. My current index is less than the index. My current index plus plus. And what we can do in here is we can just go to the next node and 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 go to the next node. So if you want index 2, I'm going to start at 0, right? 0 should be this one. This would be 0. This would be 1, and this would be 2. So 0 is my current index. 0 is less than 2. Go to the next one. 1 is less than 2. Go to the next one. 2 is 2, so we'll stop. And then we're done. We can return the current node's data. Give them back the data there. Now we probably should do a quick sanity check and make sure if my index is greater than or equal to my number of items. I'm going to throw a, probably an index error. Where is it here? There's a good error in here. Error, length error, maybe? There's probably a good one in here. Probably a length error. That's probably fine. Length error, invalid index. Something like that. So you can only get out valid indexes, right? Otherwise, I mean, we technically could just keep going next and next and next and next and next forever because we are a circle, but we're going to give them back some bad data at that point, right? We should tell them, hey, this one didn't work. So in terms of performance, with n number of items here, if you want to do some fancy arithmetic, you can, I don't know why they like to say index is k instead of I, but this would really be my number of items, or really just k here, based on my index, whatever the index is. But it's all, the further in I get, or the bigger I get, the bigger k gets, the longer this is going to take. So really we still say it's like O of n, or n minus k, or k minus n, or something in here where you get the bigger index I want, the longer this takes. So if I've got 1,000,000 items and I want item number 500,000, I have to do 500,000 operations. So this would still be some sort of linear based operation here on average, right? And this works. So the best case, if you want index 0, it takes me one operation, right? Here you go. Here's index 0. The worst case, if you want the last item, well, I have to walk through all of those to get there. That one's no good. But on average, right, if you were to get every single item in here, okay, how long does it take to get item 0? How long does it take to get item 1? How long does it take to get item 2? And average that out, we're definitely going to be linear, right? What is the sum of all the numbers from 1 to something is, oh man, what was there's fun math for that, but it turns out to be, what is it, 1 minus n or n minus 1 or something? You remember that? How to get the sum of numbers in a sequence formula. What is it here? N divided by 2? Is that all it is? Something like that. In a sequence. That sounds familiar. That's okay. We don't have to be precise. It's close. But it'll be on average n based, right, when we get there. Now we can do a very similar thing. Now we can't just say and assign a value back to the at here. This one's not going to work for us the way that this works for us. But we can say maybe set at an index the t value, and instead of returning the node data, right, we'll set the data, or maybe we'll have a old data is that one, and then I'll take the current node's data and I'll set it to the value you give me here, and I can return the old data. Right, so we can go change the value here. You can set what's here. This is probably a little easier for us to do with the function. So you can set the value at a given index here, and I'll give you back the old value here. Right, same idea, walk. Now, if you wanted to optimize this and get to slightly faster, we could look at, hey, is the index closer to the end or closer to the front? Because if it's closer to the end, we can start at the end and walk backwards, right? So if you want the second to last index, I don't need to count all of n minus 2 to get there. I could just start at the end and count 2. So we can make it slightly faster, but again, it's still going to be n-based here, even with all of our optimizations. Right? We're not going to make it that much faster if you've got 1,000,000 items and you want the center, you want 500,000. There's no way for us to speed that up. You have to do 500,000 from the front or 500,000 from the back, eventually to get to the middle there. We don't have any direct access. So linked lists are going to be much slower if you want to get values out of given indexes. But we know they're going to perform better, because there's never going to be a resizing here as we go and add to the first, add to the last. We never have a worst case of n. Now, on average, for our array-based lists, right, we know it was still constant on average, but occasionally we did have that worst case performance where we had to resize and copy everything down to a new array, like we do with our dynamic memory. Way back when, right? We're thinking that was back in January, wasn't it? Do you remember January? January was cold. It's not as nice as March has been for us. I think we're going to get more snow, though, aren't we? Isn't it supposed to snow again, I think? Monday or something? I think it was Monday. I forget. It was going to get cold again. So this is the second false spring before we have a real spring. And my birthday's in April, and it always snows in April. One time it snowed on my birthday in April, and I was sad as a kid. Because it wasn't enough snow for sledding. It was just enough snow to make it cold out, so I couldn't play outside. It's like, this is no fun. All right, so this is our circular doubly linked list here. List. So we have a list in the standard template library, right? So list lets us be a linked list. We don't have to write it ourselves. Again, this idea is it's not all that useful to write it ourselves, but we go through the process of writing it ourselves so we can better understand why it's good at what it does and why it's bad at what it's bad at. Why is it fast at certain things and why is it slow at certain things? So general list here, fast random access is not supported. Right? You can't just say, hey, I want index 27. You have to count 27 out. So this will be slow for that here. But it has all your cool operators. You can do fun things. You can get the getting iterators is neat. We're not going to spend any time doing that. You can work on that another class. Remember, we could use the beginning iterator, which really was just like a pointer. Then we can walk that pointer as we went here. Push back, in place back, pop back, push front, in place front, prepend range, pop front, resize, swap. Yeah. So we got some fun operations here, but this will be our list. So if you need a linked list, you don't need to write your own. Just go use the list template class. Did we talk about this one in Zybooks? I'm trying to remember if that was in the, I feel like that was in the list, wasn't it? Let's see. It was in here, list. We talked about this one. I think I mostly said, let's just skip over it here, right? But it was in the list. So you probably read it because I'm sure all of you are doing your reading in the textbook like you're supposed to. It's worthwhile, I promise, because I'm not going to say everything in here, and I try really hard not to read to you folks, because I know being read to is just terribly boring, unless it's like a good story. And then you can just kind of sit and chill and listen to the story. Audiobooks are fantastic. It's a good experience. Reading a technical book to someone, not a very good experience. That's not very fun. All right, so we've got our list we can use if we want. We can write our own list here. The idea of this is all using the node class. Okay. Now there's one other cool thing we can do with this if we want to take it one step further to get a little bit better performance. And sort of that's the idea here is we want to get good performance at certain things. So what we can do is we can add another class here that will let the user, whoever's using my list, interact with it at specific positions. And that's kind of fun. So that's a positional linked list. So if I use a positional linked list, what I can do is I can say, okay, when you're working with given items here, I'm going to give you a position. Now, the position class is not this sort of private inner class that we don't want anyone to touch like node. Node was this private inner class. It was an implementation detail that no one had to know about. We just needed it to write linked list. We never gave nodes to end users. We only let them interact with the linked list. So with a position, though, I'm going to give this to the user. And the idea with the position is it will point to a position in my linked list. So if they want to add 50 items here, and they can get a position pointer to say the middle, say 25. If you have a pointer in a linked list, if you have the given node, how long does it take to add something before it or add something after it? Right? How long does that operation take? Well, we have our quick little helper function. Where did I put that here? We had our add between function, right? This was in our, oh, that should have been our private section. Oops, that should be private. Oh, that was private. Yeah, sorry, that was in the private section. I'm getting a little confused. So to add something between two nodes here, does it matter how many n items I have? Like, what kind of speed is this going to be for us in terms of how many n items I have? Do I have to get somewhere to add between two nodes? No, if I know what node comes after and what node comes before, this is a constant time operation. This one's great. So if I give the user of my linked list a position and say, okay, hey, you can track this position, and I'll let you add before this position or add after this position, they can do adding at either side, forward, or front or back, of that position in constant time. And then the user can really essentially have as many of those positions as they want. Right? We can just let them, hey, if you want to track 50 different positions in your linked list, go for it. It's on the person using my linked list to decide, do they want to store more of these positions, or do they want to just have one or two? However they want to work with. So if they're adding a bunch of pieces of information to a linked list here, you can imagine, just for fun here, if we wanted to like make a list of everyone's names, and I wanted to really quickly be able to get at them and keep them in like alphabetical buckets. Let's just throw all the A's together, throw all the B's together, all the C's together, all the D's together, but I want them all in one list. I could make a linked list of strings, and then I could keep a position pointer to the A's, to the B's, to the C's, to the D's, to the E's, and every time I got a new E name, I could, hey, here's your E position here, go ahead and throw it after. And I could just start throwing them immediately at that location in my big linked list of names. That would be super fast, right? I'd have to trade off a little bit of memory, use a little bit more active memory to keep all of those positions, but I could insert like that every single time I get a name. Here's the position, here's the position. Just add it after, add it after, add it after. So you can do very quick inserts if you have a position, which is really fun. So let's see if we can make one more class here for a positional linked list. And this again will be circular doubly linked here, but will also be positional. So hopefully now I can remember to rename all the right things here. So this is our positional linked list, and I should rename the constructor. There we go. Okay. Then what we're going to do is we need to have another public class for them to use for position, because I'm going to give the user positions here. Now, I'm okay throwing it in the same file here. Generally, I don't like to do that sort of thing, but they're related, so it's probably okay. So I'm going to make let me do that up above, actually. We'll do that one first. We're going to make a template class here of type name T. This will be my class position. Now, position needs to know the node that it points to, right? It needs to know the linked list it belongs to. We can kind of quickly validate, do you belong to the right linked list here, which is nice for checking. It's really all it needs, right? So we're going to have a private section and a public section. So the private section then will have a node of type T node, and then we'll have a positional linked list of type T list. Let's see. Oh, I can't do node, can I? Shoot. I don't know if I can do that right. And I might need to put this, sorry. It's been a little while since I wrote one of these because this is really silly to do. Let me try putting that in the, why is that the public section? Did I have public in here twice? Really? That's why I was confused. That was supposed to be private. Oops. Okay, this should be the private section. No, I'm sorry, that's public node. Folks, I'm so confused. I'm so confused here. I'm sorry. There's private, there's public. Okay, all right. Private section, public section. So in the public section, let's go add another class here, see if we can do that. Template type name T, class position. Is that going to let me do this? Where's my IntelliSense? Come on. It should color things in for me. There we go. Okay, now it colored things in. Now it knows about node. All right, now I'm a little bit happier. So then things we can do with a position, we should be able to get a T, I don't know, data out. And all that's going to do then is return the node's data. Right, so you can get that data out that is referenced by this position. So if I give you a position, you can get the underlying data back out here. And that's probably fine. Should be good here. We probably need a constructor, right? So we'll add a position constructor. So position needs a node t. Oh, these should be pointers here. I'm sorry. Make sure we do pointers of the node and a positional linked list of t pointer for the list. We'll set my this node to the node and my this list to the list. Okay, so I can make a position. It will reference a node and it will reference the list that it belongs in. So if we're letting people use positions, what I want to be careful of is that you could have 3 different positional linked lists for storing 3 different sets of things, right? So you're going to get a position out of each one of those. So if the end user gets confused and gives me a position that doesn't belong to my linked list, and they try and use it in my linked list, weird stuff is going to happen. So I have the reference, I have a pointer to the list it belongs to, so I can quickly validate inside the function, should it be doing this sort of thing here, right, when I use it in my lists. Right? So we've got set, we've got at, we've got this. Now I want a way to get positions. Right? So I'm going to have a position of t pointer, we'll call it first. Come on, turn green. Did I spell it right? Position? I spelled it. Okay, maybe we'll figure it out here. So to get the first item out, then I'm going to return a new position. Why? Oh, because I have to probably have this above, don't I? Let's put this above. Okay, now it recognizes it here. So new position, given, so the first node then is going to be my dummy nodes next. That's the first node. And then the list is this, right? This is myself, right? This is the linked list here, the positional linked list. I can give it a reference to myself, right? This is a pointer here, so I can give it this, and I give it the dummy nodes next. So now they have the first position. They could do a position of t for the last item here, and it returns dummy nodes previous. Right? So I can get the next, I can get the previous, we're good to go here. Then other things I can do with a linked list, I could ask for the position of t after a given position of type t pointer position. So what comes after this position? Or should we call it next, previous, after, and before? What makes sense? I don't know if we want to, return what comes after this position. What comes next? What comes after? So the first thing I want to do is make sure that the position is one of my positions, right? That it's part of my list here. So I'm going to check and say, hey, if my position dot, oops, I need a way to get the list back out here. Where's my position? I should be able to get a list, shouldn't I? Position.list. Position.list does not equal this. I think it's letting me do that, right? It's not coming up with an error. So if my position list is not this, right? So the position knows what list it came from, and I know what I am. I know my this pointer here. So if those don't match, I can throw a, I don't know, some sort of logic error, probably. This position is invalid, or is not from this list, or I don't know. You can come up with some sort of error message letting the user know you shouldn't use this position in this list. Because if you have 3 different positional lists, maybe you've got a list of names, maybe you have a list of birthdays, maybe you have a list of favorite colors. Right? You can't take a position from one of those and use it in the different list. It just won't work, right? If it does then work, I want to get the position that comes after this one then. So I can return a new position that position, right, its node that it should point to will be this position dot node dot next. Still this for my linked list here. Right, go to the position, grab its node, grab that node's next value, right? Whatever's next here, and return that one. That's what's going to come after. We're going to put that one after. Now, we want to be careful. At some point, we might run into where we've completed the full circle. We don't want to give them back the dummy node. Dummy node's not really super useful to give them back here when we're doing this. So we probably want to have some way of checking to make sure that the pointer, the node pointer, is not the dummy node when we do this here, right? That might be useful. So we can have a, where's my private section here? We can have a position of t pointer make position. Is that going to let me do that? It's not part of this one here. Okay. It's probably not proper, but I got to put it after this one so it knows what the position is here. So we're going to make a position of t pointer make position given a node of type t node. So I can make a position given a node. This will do that validating for me first. So I want to make sure. So if my node is equal to my dummy node, I'm going to return a new position. Oh, actually, I'm going to, because this is a pointer, I'm going to return a null pointer. This is no good here. You've reached the end. Bad stuff. Right? It's not a valid node, not a valid position. It's not good here. Otherwise, I can return a new position given the node and given this here. Right? So in each of these, then I can return my make position. So first will be my dummy nodes next. So this will check for me if I'm empty, if dummy node points to itself, because I'm empty here, they'll get back the null pointer, right? And I can do the same thing with make position given dummy nodes previous. So to what comes after then, I can return a make position of my position's nodes next, right? Go to that position, go to its node, go to the next node of that one and turn that into make position. So if it hit the dummy node, I got to the end and I hit dummy node, they'll go back to the null pointer. There was no good here. Same idea with before. What comes, maybe if you want to say before. So before a given position, return dummy node, the nodes previous. Right? Again, quick little check, make sure it belongs to this list here. Excuse me. Should be pretty good here. So I can get what comes before, I can get what comes after. So the person using my positional linked list now has a way to go through and get every value out or keep these positions around if they want here. So let's see if we can make one more list here. We'll see if it even compiles. So let me see if I get any build errors. Hey, okay, we didn't get any build errors. That's a good sign. So we'll make a positional, oh, we got to go include it first, right? We'll go include a positional linked list. Okay, now we'll see if that compiles. Now I've concluded. Okay, good, good, good. I'm all worried it's not going to work, but so a positional linked list of, we're going to do string here for names, and then names dot. I can. Didn't I have add first, add last? Why aren't those showing up here? That's the public section. Names dot. Oh, there. I typed in P is why. That was my bad. So we want to add a couple things here. So we'll add some names here. We'll add Eric. Names dot add. We'll add last, I guess, to this one then. Jub. Add last. I'll add VB. Okay. So I got me and two of my kids here in a list. So I should be able to get out the first position then. So if I want a position, positional linked list of position. Oh goodness, here. What do I get? Auto of my names dot first. auto. Oh, so this will be the current position is names.first. And it is a positional linked list of type string is the scope, right? And then the type is position string, and it's a pointer. Lots of fun. I'd rather just type auto. That's a little easier for me here. So I should be able to see out then my current position dot data. I should be able to get out the data, right, from that position. Or really I can say while my current position does not equal a null pointer, let's print the data at that position. And then I'll say my current position can equal names.after my current position. So, okay, give me what comes next. Oops, what is it? Names.after. Don't I have after? Oh, I wasn't returning a pointer. That's right. First and last need to be pointers. After and before need to be pointers. There. So if we make the types match, now I should be a little happier. So ideally, we should be able to get the position out, get the data, go to the next one. Get the data, go to the next one. Get the data, go to the next one here. Let's see if that one works for us. Oh, now I get build errors. Okay. Turn, what? Left of data must have a class struct union. This node data. There we go. Let's try that. No? What do we do here? Left of list must have a class struct union dot list. Position. Oh, because it's a pointer. Sorry. This position. Oh goodness. Let's see. Position. I changed it to the pointers and now they got upset with me. No. We're almost there. Can't access a private member declared in position. So I can't get at the list because list is private. Okay. Shoot. Now let's make them public then. We'll just cheat. We'll make those, just put those in the public section. There's probably a better way to do this, but that's okay. This, again, is just an exercise. Not super concerned. Let's try that. Nope, okay. Oh, we're so close, we're so close. So the nodes next, right? Nodes previous. Pointers, because they're all pointers. Position of type T. There we go. Hey, okay. Fix all those errors here. Pointers are obnoxious sometimes, I'm sorry. We get Eric, we get Jeb, we get Vivi. We get them back out here. And then it stops when that position became null. Right? We've essentially built our own iterator, right? Where we could create those iterators. We could say, hey, I want the beginning iterator. We've kind of redone that ourselves with these positions. That's what that iterator lets us do, right? We're sort of building, here, I'm going to give you a pointer to a given place. That's what that iterator was, right? It was a pointer to where it was in that list, that collection, as we went here, right? Then, now we can iterate through these things. I can say add before or add after. So I can take a position of T, add before, given a position, pointer, T the position, and then the T data. So if you want to add something before a given position, right? I can make sure my position's valid, and then I'm going to take my add between function, and I'm going to add between the position node and the previous node of that position. And I'm going to add before this one here. So I can add between my positions. So what comes next then? So if I'm going to go before this position, what comes next will be this positions node. Right? What comes before this one is the positions nodes previous. Right? I'm going to go add that between. Oh, I need the T, the data, right? So add a new node between these ones here. And then because add before, I'm going to give them back a position from doing this here. I'm going to return a make position given my positions nodes previous, right? I just added it before me. So that'll be the node I want to return as a position. So it creates a new node between this positions node and the previous node, right? And then returns the new node position, right? And I can do the same. I can add after a given position. So instead of going, what comes after will be the nodes next, right? And what comes before is the node. And what I'm going to give them back is the nodes next. I grab the next one. And I feel a little bad I have the same validation more than once, right? I have this same check every single time. That one's a little bit sad, right? So it might be nice then, right, if we could refactor this, right? Turn this into a little function. I don't want the same code more than once. So let me go quick actions refactoring. I want to extract as a function. We'll call this validate list or validate position. Sure. So now I can do this as a validate position every time. Oh, it didn't pick it up here. It should have picked it up. That's okay. So we'll validate position all these times here. And then let me throw this one up. This one can definitely be private. Right, we can validate that position. And then we have to do a lot of typing here because every time we validate the position, right, we're using that node. So would it be fun if this one then returned the node? Right, what if we had a node of t pointer that we returned? And then so if it is valid, then we can return the positions node. So every time I validate my position, I can say my auto node is this, and I can like skip one step here. I don't know if you like this any better, but it saves a little bit of typing if we plan this ahead of time. I just get right to the node every time. So now it's like the node and the node's previous, right? Just keeps you from having to type the position pointer every single time, which is nice. And the node. All right, so I think that should still work. Let's see. Oh, where's my build error? Uh-oh. Position is not defined. Identifier not found. Oh, goodness. All right, I'm going to just move that. I think if I did all my prototypes like proper way, this would probably work, but I'm tired. I don't want to bother with that. Is that okay? Let's see if that works now. All right, okay. So now I should be able to get a position out. And if I want to add something before or after that position, excuse me. So if I have the first position is my current position, and I want to add something after that, right? I should be able to take my names list, and I want to say add after my current position. Oh, the data first. Let's add Joy. I forgot Joy. So we'll add Joy after the current position. Right? Add after is a string. Oh, I have them backwards here, the position and then the value. So I'm going to add Joy after, and then the loop should still work, right? Because I still have, this was first, now Joy should come between Eric and Jeb. Right, when I loop through it, let's see. Eric, Joy, Jeb, Vivi. Cool. If I want, so I didn't save the position, right? If I wanted to, I could have this was Joy's position. Position, sure, that's probably spelled right. If I wanted to, and you could keep different pointers at different places, right? The idea is I could have lots of different positions as I go. Now, we could also then have a way to remove a given position, right? We don't have a way to remove anything yet. We haven't bothered with that, but if I have a position, right, we have the private function for remove the node and jumps it out of the list here, right? We never really let anyone use that. We had pop first and pop last. So we could remove the first and last here as we go, which is good. But maybe if I wanted to remove an item at a given position, we could add that in as well, or we could add in here, let's replace the data at a given position. So we've got lots of other fun things we could do with them if we wanted. Right? Now that I can give someone positions, they can start using them. Excuse me. The problem is, if you remove a node and you still have a position that points to that removed node, we need a way to know that it's no longer valid. So if I went and I added Joy in, right, she's valid, and then if I wanted to say, go, let's take it back out later, I still have a position that points to that node. That would be invalid. We need to make sure we clean that up. So one of the things we can do is we can make it point to itself. So when you go to remove a given node here, you can make it point to itself, and a way when we validate our nodes, we can check, hey, if it points to itself, it's not valid anymore. There's a quick way to do that. Ooh, that's actually, we're deleting the whole node. Excuse me. That'll get really screwy, won't it? Because we're deleting. So again, it's just a bit of a thought exercise playing with this here. I don't think we need to go through and write all of the code for it, because writing it by hand is terribly dull. It's not all that interesting. And we've got libraries that do this for us. Right? We don't need to come up reinvent the wheel because we have the list operator, and the list operator has its own iterators. Right? We can already use iterators here, which is super fun, and you can do all the things that you want to with it, which is really cool. So just kind of experimenting, playing with this, looking at the speed of given things here. So first and last, right, are always going to be O of 1, because we know where those things are. There's no walking that has to happen here, right? Getting the position that comes after is also O of 1. Right? Doesn't matter what position you're at. You could be in the middle of a 10 million item list here. You want the position that comes after this position? It's constant, right? Because I just go to the next link. It will always run the same amount of code every time. That one's O of 1 as well. And same for adding before and adding after, right? Even if you have a million items here, it will never have to do any resizing. So positional linked lists are great if we're going to be doing a lot of adding and removing from specific positions, because the person using my linked list can hold those positions and add before and add after. Right? They can quickly insert things anywhere they want in the linked list if they're willing to keep the positions around. Now, adding something at a specific index is going to be slow because you have to go count to that index. Or getting something out at a particular index will be slow. They have to go count to that index. But if they keep these positions around, they can really quickly get at whatever is there at that position or on either side of that position. So it gives them the flexibility. If they want really quick access to these things and really quick inserts and deletes from a given position, we can give that to them. So in certain cases, this is a very fast and efficient data structure. Are we going to use it all the time? No. In fact, a vector is probably just easier most of the time for us. We don't have to worry about any of that sort of stuff. But if we know we're going to be doing a lot of adding and removing, we know vectors can be slow at that. Right? If you try and add something at a particular index in a vector, or remove something out from a particular index in a vector, it's really slow. Everything has to shift and fill back in, or expand, and you have to copy things out. So this is a more flexible data structure if you're inserting and removing from the middle versus the vector here. All right, so I think that's probably good for today. That got through the rest of our, so this will be our positional linked list. We got through that. So next week we have the project due, right, coming up. So that is our checkers project is due next Tuesday. Right, so we've got rest of today, the weekend, 9:30 in the morning. I keep getting emails from people thinking that things are not due at 9:30 in the morning, and I'm really confused why people think they're not due at 9:30 in the morning, because they've always been due at 9:30 in the morning. I guess it was confusing at first because the quizzes aren't due at 9:30 in the morning. My apologies, the labs aren't due at 9:30 in the morning, but the projects are, right? They're in Canvas, and they've always been in Canvas, but that's okay. Right? We'll get through it. It's okay. But 9:30 in the morning, so I'll go over the checkers solution first, and then we'll talk about the next project, which will be our last individual project after checkers. We'll have one more project. Will be our individual project, and that'll be due April 2nd or so. But I still want to start the group project this week, just so you have a little bit more time on it if you want to have a little bit more time on it. for our group project. We got a little bit behind when we bumped things out over break. It's okay, it won't be the end of the world here. And then we've got midterm review. Should be pretty quick and easy. I'll give you last year's midterm, or when did I teach this last? The last time I taught this class. It's not coming to the top of my head right now. I'll give you that midterm, so show you what it looks like. I'll give you some example questions so you can see how I write the question. So it's going to be half quiz questions and then 3 short or longish answer coding questions. They're not big, they're not projects, they're just, hey, write some code that does this. So the idea is you could sit and take it in an hour and 15 minutes. I'll give you 90 minutes for it, but you can take it anytime you want, starting 3:21, as long as you turn it in before 3:26. So if you don't like to take tests at 9:30 in the morning, please don't. Right? Whenever you want to sit and spend 90 minutes on it, go for it, whenever it's good for you, between 3:21 and 3:26. So I don't plan on being here 3:21 in the morning, unless you really want me to sit and watch you take a test. I will do that. It's a little weird, but sure, just let me know. Other than that, I won't plan on being here in the morning for that. So it'll be do 3:26. Yeah, so 3:19 we'll go over checkers. We'll talk about the next project, and we'll do the midterm review. I was going to post it today. That's right. So you can actually go look at it. So let me go pull that up real quick. Let me go find it. 200. When was the last time I taught this one? Is it summer 29? No. Fall of 20. Okay, yeah, fall of 22. They sort alphabetically instead of by year, which is the weirdest thing here. But I guess that's kind of a default sort, I suppose. So fall of 22, then I had the midterm. Let me go preview this one here. So let's see, I think I can print this as a PDF, right? That's probably easiest. I'll do that. Okay. So print as a PDF. Make sure it looks like I've got all the questions. It's a ton of pages here just because everyone is a text box here. I'm sorry. So it's not actually super long here. Let's go to my desktop. Where did that go? Oh my goodness. Come on, desktop. So this is CIS 200 practice midterm. All right, and I can go back to our class. I may just go drop this in files here. This is the practice midterm. All right, so let me go over it just real fast with you real quick. Canvas will be slow to load. So first point is agreeing to the academic integrity policy. Someone actually did a study on this, which I find super interesting because humans are complicated people. If they asked before they took the exam, it's like the first question essentially, or like a cover sheet kind of thing saying, you're not agreed to not cheat. People would be more likely not to cheat than if they asked at the end of the exam. So they did, their little randomized sample here. They had half the people got it before question, half the people had it at the end. So at the end of the exam, the last question was, put your name down to acknowledge that you did not cheat. And if people had cheated, they were less likely to admit it. They're like, oh, well, I already cheated. Shoot, I'm just going to put my name down anyway and lie about it. But if you ask people up front, they're actually very likely to not lie and to not cheat because they've agreed to it. So humans are really funny. So if you put that in your head first and say, hey, I'm not going to cheat on this, most people don't, which is actually really cool. Like it just works. And then these are all quiz questions, right? I literally take them out of the quiz banks. I call them quiz style questions, but I just repeat quiz questions. So you get 14 quiz questions come back at you here for those. And then 3 long answer questions. So it's 30 points total. So 15 points on the quiz questions, or the 1 freebie and then 14 quiz questions, and then 3 5-point questions. So this one was write a recursive function that accepts vectors of integers and returns the sum of all values in even indexes minus the sum of values in odd indexes. And I'm just flat out telling you, you want to use a helper recursive function for this. So it doesn't need recursion to do this, but I'd like you to do it with recursion just as an exercise. Right? So you're going to have to pass in what are your current indexes as we're going through this. What are the values you're looking at? Right? Any way you want to do that, and we'll go over a solution on Tuesday, but kind of think about it here. So if I passed 4, 2, 7, 10, 11, I would get 8, which is 4, 7, and 10 added together. Right? Those are the even indexes, 4, 7, and 10, minus the odd indexes. Right? So just this is an example of using a recursive function. which is essentially just a loop. So something on recursion, you get a question. Write a function that accepts a two-dimensional vector of integers, returns true if the sum of each row by index matches the sum of each corresponding column by index. So the sum of row 0, is that the same as the sum of column 0? Is the sum of row 1 the same as the sum of column 1? Right? Is the sum of row 2 the same as the sum of column 2? So just working with two-dimensional vectors, two-dimensional arrays. I will do vectors because I don't like arrays. I think vectors are just better. That's just me. Other people will tell you different, and that's fine. Just smile and nod. You'll all know vectors are better. So question on recursive functions, question on two-dimensional vectors. And then the last one here is writing a class with extensions, with inheritance. This one is not super long. It takes a little bit of typing, but that's okay. So we're going to have a class for midterm that has attributes for name and score, get methods for both, a constructor that accepts both as arguments. Don't have a no-argument constructor. That was on purpose here. And then we're going to extend that as an easy midterm, and we're going to override get score to just return 100. There is no like value that we're looking at for 100. We're just going to override this to always return 100. So just a really pretty quick. This will be probably 20 lines of code here. Most of them are curly braces at this point, right? With just some basic gets and sets. Not a whole lot of arithmetic. So question on inheritance. Those will be the 3 long answer questions you'll get on the midterm, okay? And we can go over these on Tuesday as well if you want to spend a little bit of time, play with them yourself if you want, and I'll go over answers on Tuesday. That sound good? All right, awesome. So if you got anything else, let me know. Try not to wait until Monday night to ask questions about the project. It happens all the time. That's okay. I get it. I wait to the last minute for things too. That's why you don't have a lot of scores yet. My apologies. I was going to do it over break, and then bad stuff happened, and I kind of lost my break. So I'll get those in for you. But hopefully you've been doing the self-assessments as well. So again, most of the time I just give you the score you give yourself on the self-assessments. So when you looked at, I think I asked you to do these with the self-assessment using the rubric. So just go through the rubric and say, I got 5 points for this, or 4 points for this, and 3 points for this for each item. Tell me how you did. Folks are really good at scoring themselves. I think I forgot to ask that for Project 0. I think I did for Project 1, though. So however you think you did, unless you just flat out lied to me and said, yeah, I got full points for everything, and you have like nothing in it, which is rare, like maybe once a semester someone does that. It's like, they think they did everything perfect. I'm pretty sure they know they didn't do everything perfect because it wouldn't even run. The one time someone tried, it's like, your code doesn't even compile. How can you tell me you got all these points? Like if your code won't even compile. But again, generally, I'll just give you your self-assessment score. Oh, I forgot to ask for this one too, shoot. Yeah, maybe I'll ask you to add those in for me. That might be it. Let me throw an announcement out there. Let me do that. So please, self-assessments. Please add a self-assessment your README files for project 0 and 1. Sorry, forgot to ask for it earlier. There we go. Thanks. It's fun when someone like talks to themselves out loud while typing, right? Drives my wife crazy. I don't know if it's just me. My brother does it all the time. I don't know if I learned it from him because I do a lot of things my brother does. But I will talk to myself as I type and like mumble. Usually if I'm just home alone, it drives my wife crazy. Why are you talking to yourself? But all right, anything else? Feel good? Awesome. Well, have a great rest of your weekend then. Take care.